BC Calculus, Lesson 2.4, Rates of Change and Tangent Lines. I apologize again for my voice. Just decided to go out on me. Must have the air conditioning on too high in our house. All right, so we've discussed average velocity earlier. Let's play with it again. Find the average rate of change over the interval. Well, what that means is we need f of 3 minus f of 1 over 3 minus 1. What's the final velocity minus initial velocity divided by how long it takes to go there. So we blast this out on the calculator. And I believe we get 24. No, 27. No, 24. Minus 0 over 2. 12. And now we get some units going. It's going to be velocity, so it's meters per second, feet per second. Since this is America, we do feet per second, which we really shouldn't. We should be doing metric. Spoken as an engineer who's played with those numbers for quite some time. Now we graph the situation, and the graph doesn't look exactly like this. It looks something like this. So we say here is 3, and here is, actually I think 1 would have been right there. And this is f of 1 here, and this is f of 3 here. And if you connect these lines, you can see that what you're creating is a secant. Something like that. And you're approximating what this actual slope would be. This would be tangent. And this is what calculus derivatives are all about. We just use the secant line to get there conceptually. As we get closer and closer and closer to the point we want, we will get a tangent line. So how do we find that? Well, now you've got the tools. You've got limits. The curve we used earlier is actually a little bit challenging for this purposes, so we will give you an easier one. And we'll say at x equals 2. Now I actually will bring this into play last. We do the limit as some variable h goes to 0, and that's going to be the difference. That's going to be where the secant, the x value on the secant curve gets smaller, smaller, smaller. And we will do x plus h squared minus x squared over h. More on where this formula comes from later, but if you look at it, it's doing exactly what we did above. The y value, the functional value at the bigger value minus the original, all divided by the total. So we do a little bit of algebra here. X squared plus 2xh plus h squared minus x squared all over h. X squareds cancel. We factor out the h times ah, 1h plus h over h. Just realized I forgot to write my limit. Drive h to 0, and we are left with 2x. And that is the slope at any spot on the tangent line. We want it at x equals 2. Slope will equal 4, and again, feet per second, meters per second, even though I haven't defined any of that for this question. I just think it's probably a good idea for you to start getting used to thinking about velocity units. So that was a specific example, and this is the general, and this is what we just did. The slope of any line at a point, instantaneous slope, is this limit as h goes to 0 of f of a plus h minus f of a all over h. And the tangent line is the line that goes through P with the slope m. So at this point with this slope, and we can just go real quick and write it as point slope, which I will very soon do. Now this one's a tough one. I took the easy way out previously. Now I get to pay for it. So we need the limit as h approaches 0 of 1 over x plus h minus 1 over x all over h. Common denominator, x's up here cancel, h's will cancel, but we'll come back to that. Well, no, we'll do it now. There's only an h left, so they're gone. So we get 1 over x plus h times x. And I have made a mistake. Yeah, I didn't distribute my negative up here. And you would say, well, who cares? Well, they cancel because they divided, so I still got a negative 1. As h goes to 0, big deal, we get negative 1 over x squared. And for the x equals a point, we get slope is negative 1 over a squared. Now it says describe the tangent as curved. Well, since a is squared, no matter what I put in for a, the tangent will always be negative. A cannot equal 0 because it'll fail. And as we get closer and closer to 0, get really steep slopes. Further from 0, we get out towards the horizontal asymptotes. We get really flat slopes. So this is called the difference quotient, and I wish I could explain to you how much you're going to be using this. It's absolutely critical. I just went and did a bunch of homework problems, and I got used to writing out the process I just went through. And there's several tricks for algebra. You've seen 2 of them so far. For trig, there'll be some trig identities we'll need to pull, and then we'll tie it all back together at the end of the year. But for the time being, that gives you pretty much a good idea what's going on. Just to give you some algebraic practice, we can also do this for a normal line. We do everything the same until we get to a certain point. Limit as h approaches 0 of 4 minus x plus h squared minus 4 minus x squared all over h equals 4, I gotta be careful here, minus x squared minus 2xh minus h squared minus 4 plus x squared all over h. Oh, we got a bunch of stuff's going to cancel here. With the 4, negative x squared. We can pull an h out of here, here, and here. And we are left with the limit as h approaches 0 of negative 2x minus h, which is just negative 2x. We want to know it at x equals 1, so we say the slope is -2. They ask for a normal line though. So what do? Well, it's easy. Normal line is perpendicular to tangent line. So m of the normal line is equal to 1/2. And I said I was going to do this earlier, and I meant it. I like to find the point up here where it's nearby. I'm going to put in 1, and I'm going to get a 4 minus 1, 3. So I'm going to use that point 1, 3 to go. Y minus 3 equals 1/2 x minus 1. For some reason, a lot of the textbooks I've seen prefer to have the y alone, but they don't distribute and put it into slope intercept. So get used to doing this. So now we know how to find the instantaneous rate of change. Find the speed of a falling rock at t equals 1 if the position function is yada yada. Well, like I said, I like to find the limit and then plug in my value later. So we have 16t plus h squared minus 16t squared over h. So 16t squared is going to cancel. I'm not even going to bother with that. We'll have 16 times 2, 32 th plus 16h squared all over h by, we get equals 32t. Put in t equals 1. We get a slope of 32 feet per second. Again, no units, but get used to doing that. A little disappointed I didn't put the units in, although I do know that's an old problem that we had, feet and seconds. So get used to doing this. You're going to do it a lot. And it's the definition of a derivative coming. So you want to know what it means. You want to understand the difference between tangent and all that. That is it. Happy mathing.